right now what we are going to see is some additional components of the processing framework that we can use to use the same algorithms we did yesterday, reprocessing or calculating a slope or using the raster calculator, but in a more efficient way sometimes. So we need some to automate some process, we can do it. And as an example of that, we're going to see some hydrology analysis. Then we're going to try to automate all that. So we're going to see some hydrology analysis that involves several steps. Okay, we're going to work with my sample data sets, the same one that I gave you. But then we're going to try to do the same thing with a different data set. So that would involve taking that data set and going through all the single steps, right? And instead of doing that, it would be good to have everything in one single big step, right? So if someone comes with a new data set, it's like, I want this calculation, and you don't have to go all the way. You just do, okay, I want to go from here to there. And just put all that into one single step. So the idea is to make kind of like a small new program, like a new algorithm, but you don't have to program. You do it graphically. Right? And you just put the relation between your algorithms and you define a workflow, right? So I'm going to start with a very basic exercise about hydrology that just involves 2 or 3 steps. Put that into a model. So we're going to see the modeler. Then I'm going to do a more in detail hydrological analysis, which involves more steps. And then the idea is that you are going to try to put all that long hydrological analysis into a model yourself. Right? And then I will give you some time to do that, and you will have to define your own workflow, right? So the first thing we're going to do is to open our data set. And that's the one called hydrology, which just contains one detailed elevation model, which you should already be familiar with, right? And we're going to calculate a very simple parameter, but it's a very useful one, which is called topographic index. Basically, there's an algorithm that comes from Saga as well that is going to calculate 3 different indices that analyze the topography based on 2 elements. One is the slope, and the other one is the catchment area. The catchment area, if you remember, we haven't calculated the catchment area yet, but yesterday in one of the examples that we saw, there was a layer with the catchment area, also called accumulated flow, right? I'm going to explain what that means, right? So we're going to calculate these topographic indices, and they require, as I said, the slope and the catchment area. So you can look for that in here. Yeah, topographic. That should be that's the topographic wetness index, right? You see that one? Let's see if it works. Okay. So you see in here, this is the algorithm. You should understand this structure of the dialog, same as all the other ones that we have been working with. And there are 2 inputs, right? One is the slope, and one is the catchment area, right? The slope, you understand the idea, right? The slope. The catchment area, I'm going to explain now what it is, but it's something that also depends on the relief, on the terrain, right? So we can generate the catchment area from the detailed elevation model, right? That's the idea you have to know. So I do not have the slope in here, and I do not have the catchment area in here, right? So that means that I cannot run the topographic wetness index because I do not have these inputs. But I have something, the DM, that I can use to generate the slope. You did that already yesterday. And I can generate from the DN my catchment area, right? So if I do a small, where it is, the eraser? Oh, yes. Just to summarize that, I got my DM, right? Okay, so from that I can calculate the slope. From that I can calculate the catchment area as well. And then I can take those 2 together and calculate the topographic wetness index, right? That's the workflow that I have to follow, right? So I have now my detailed elevation model. If I want to do that, I have to go to the slope algorithm. Remember, we saw it yesterday. I have to go to the catchment area algorithm. I'm going to explain it now. And then I have to go to that topographic wetness index and run it with these inputs, and I get the final result. That means that if I want to go from here to here, I need 3 steps, right? 1, 2, and 3, right? I can do it with my detail elevation model, and then if someone comes with a different detail elevation model, I should go through all the 3 steps. The idea is that we are going to tell processing about this big process, big workflow, and it's going to be able to do that in one single step, right? So that's basically, we're going to automate all that. So we are going to create an algorithm that goes from the DM to the TWI directly, right? Without having to do that manually each time, okay? First thing we're going to do, we're going to run the 3 algorithms separately so you can understand the idea and how each of these algorithms work. And then we will go to the modeler. So the first thing that I need is the slope. This shouldn't be difficult, right? We did it yesterday. Remember, there's this algorithm called slope aspect curvature. It generates quite a few layers. All of these layers come from this morphometrical analysis of the surface. Okay, and just basic dialog, you just have to input, and then there are several methods, and the one that is selected by default, that is considered to be the best one. But anyway, it's not important. We can use any of the methods. It's going to generate a slope layer anyway, and that layer I can later put it into my TWI algorithm, right? The important thing is that if you have a slope layer that you don't compute it yourself, or you did it in the slope command from Goodall or from GRASS, and you have in other units, if we are going to use this SAG algorithm, it expects the slope to be in radians. So that's important, right? For yourself, if you are going to do something, you can take your radians and convert them. But if you have a slope layer that someone gave you, like this is a slope layer, and it's in percentage or whatever, you have to convert it to radians, right? Because the SAG algorithm expects the slope to be as it is being produced by the slope algorithm, right? In this case, we are using SAGA both for calculating the slope and for calculating the topographic index. So they are going to be in the same units. We don't have to worry about that, right? Okay. So that's it. We just have to run it. Nothing new here. And we just get it. Yeah. I can get rid of all the other ones. I'm not going to explain that in detail. The aspect, I guess that everyone understands what that is. The orientation, if it's facing north, south, wherever, right? And then the curvatures are a little bit more complex, but I think it's not worth getting into detail now. Remove. Okay, so I got the first piece right now, okay? I'm here. I already did this, right? Now I can go to this other place in here. And that's another algorithm that is going to calculate quite a few layers. And I'm going to use that, right? So if you go to the catchment area menu, if you search for catchment area in the processing toolbox, you're going to find several different ways. Like the SAGA, this is one thing that you can find in SAGA normally, is that when there are different algorithms to do something, they don't pick up one of them and they just implement that. They try to implement several algorithms. And for calculating the catchment area, there are several different algorithms with several different approaches. Some of them, in the end, they have the same result, but the algorithm is different internally, so they're implemented, both of them. So in our case, we are not going to worry much about it. We're going to go to the catchment area parallel, which is just how the algorithm works. It's a parallel algorithm. That means that it's going to go from the uphill to downhill in the calculation. The recursive goes the other way. It starts from the cell and it goes uphill, trying to find out the catchment area. That's not really interesting. So we're going to go into the catchment area, parallel one. That's the one we're going to use. And the idea of the catchment area, I think I explained it yesterday. It's if I stay on any pixel in my detail elevation model, the idea is to know how many other pixels are flowing into that one, right? So I have I'm going to make another drawing here. So if I have all my pixels and I know the elevation, right? Imagine this pixel, I say, okay, where is the water going from here? I just have to know the difference in the elevation, and the water always goes the maximum slope, right? So from here, let's say the water goes to that one, right? And then from this one here, and then here, and then here, right? I do the same from here. So this one goes, let's say, to here, and then it follows the same way, right? I do that for all the pixels, and then in the end I just count. Which is the accumulation in here? Well, it's 1, because this is coming from here. Then it's 2, 3, 4, 5. That means there are 5 cells that if there's water in those cells, eventually it will reach here, right? That's the idea of the flow accumulation. How many pixels I can find upstream that are common to that pixel, right? This is a very interesting parameter, actually. It's going to be used for many things in the hydrological analysis. It's one of the big differences between making hydrological analysis without a GIS, like classical hydrology, and doing it with a GIS and heat elevation model, because this is one parameter that if you don't have like a heat elevation model and a lot of computing power, you're not going to be able to calculate that. A classical hydrology, this is an idea like you can measure more or less the water that flows to a given point, you know, the area of the watershed, but you cannot do like a general thing. You know, you need a lot of computing power. So without a computer, this is not something that belongs to classical hydrology, let's say. And this is a parameter that we are going to use for many things, right? Because you can get the idea, and you saw it yesterday, those points where the catchment area is high, that means that a lot of water is coming. When a lot of water is coming to a pixel, it's going to erode that pixel and it's going to create a river. So basically that's explaining more or less how rivers are created, right? And those areas with high accumulation, high flow accumulation, those are the areas that we're going to consider as rivers, actually. We will see later in our hydrological analysis how we're going to use the catchment area or flow accumulation to define rivers, actually, as the criteria for defining rivers, separating those areas that are not rivers from those areas that are rivers, right? In this case, we're going to use it for a different thing. We're going to use it for the topographic index that I will explain later. But anyway, we have to calculate it, and we're going to use it for many other things. Let's go into that menu. You will see that, oh, whoa. Yeah, that's what happens. Okay, so you can see that there are like many parameters in this case. I'm going to try to make this a little bit bigger. But we don't have to worry about most of them. Like the outputs, there are many outputs, but we're going to just forget about most of them. We're just going to focus on the parallel area. If you select some of the other catchment area methods, they generate a different set of layers. All of them generate the catchment area, but some of them have like additional layers. Anyway, it's not something that we have to worry about now. It's just getting too much in detail. So the basic thing that I need for the catchment area is just the heat elevation model, right? If I want to know how water moves, the only thing that I need to know is the terrain, right? The elevation, right? To apply that, the water moves in the direction of the maximum slope. That's basically how things work, right? I'm going to skip that one, the sink routes and weight. But there's one thing that in this DM that I gave you, I'm skipping actually one step, because in this DM that I gave you, it's already pre-processed, and I'm going to explain you what that means. So then when you do it yourself, you have to add an extra step. But I'm skipping it because I know that this DM is hydrologically correct. Okay, when I have my pixels, what I do is like water flows into the maximum slope, right? Downhill, that's clear, right? So imagine that these are the cells that I have in here, and I have this elevation, right? Okay, if I put water in here, where's it going to go? You don't know where it's going to go. There's a hole, right? So water doesn't flow uphill, it has to go downhill, right? What happens really, if water comes here, it's going to fill up the hole, and then it's going to keep on flowing, right? But the algorithms that we have implemented in here, they don't consider that. They just analyze the relief, the terrain as it is. They don't simulate that process. So one thing that has to be done with the DDM before actually working on hydrology on it is to fill these sinks, right? To fill that. And if I fill it to 1, right? Say, okay, I just fill it. Now where it flows, it's flat. You know, if the terrain is flat, things do not flow. But if I have elevation here like 2 and water is coming that way, and here I have something like that, well, it's like the idea is that it should flow that way, right? Okay, so I have to do some extra analysis. Okay, that is done by these algorithms that are called field syncing algorithms, and you can find them in Saga as well. You know, field syncs, right? As I said, I'm not running that because I know that this DM, this example DM that I'm giving you, it's already corrected. So it doesn't have any sync, right? But normally you should run your field sync algorithm before doing your hydrological analysis, right? As I say, I'm skipping this, just to let you know. Okay. There are different ways of doing this field syncing. One is actually filling the sinks. Another one is to know where actually the water is flowing, so I get the sink route. So even if they're not filled, I know how to move the waters to the sinks. I'm not using that, and this is something that we hadn't seen before in an algorithm, that some layers I have to select a value, some layers are optional. And you see this is an extra value called not selected, so I get all the layers plus this not selected option. That means that the layer is optional, right? So I don't actually have to use it. Another layer that I can add is the weight. And you imagine that if I have the drawing that I had before, like, you know, all my flow coming to a point, and I want to calculate the amount of water that reaches a pixel, I just put all the pixels that are coming here, right? But in some of those pixels, maybe it's raining a lot. In some others, it's not raining a lot. So I can weight the pixels, right? And I can use this weight thing. That's an additional stuff that I'm not going to use at all. So I leave it as not selected. The same with the material and target. Those are extra parameters that, you know, I can use to get a more realistic, let's say, simulation of my catchment area. But I'm only interested in knowing the area, actually, how many pixels, just the count of the pixels that arrive where I am, right? There are some other parameters that I don't want to get into much detail in that, right? The only important one is the method in here, the method. And you see there are different methods, and this is for a reason. If you use any, not in here. If you use like ArcGIS or most of the GIS that have some kind of hydrological analysis, they only implement the first one. It's called the deterministic 8. And it's called that way because if I have water in one place, it just goes like that, like a straight line into one of the 8 cells that are around it, right? From one pixel just to one of the other pixels, right? And the water flows like in 40 degrees angle. So it's like flow like that, but it doesn't flow like that. And what it doesn't do is like flowing like that, which is like really does, you know, water doesn't flow in a line. You know, it can, you know, converge or diverge, right? All these other algorithms, they try to make it more realistic. So water can go from one cell to several different cells, right? So they are more complex, right? But, you know, just if you want to use the deterministic 8, it's fine. We can use any other algorithm. That's not a problem. Just, I want you to give you the idea that the D8 is the basic one, and the other ones just try to better simulate the flow, actually, how water flows into the television model. I'm gonna select the basic one anyway. Right, so we just skip all the stuff in here, not interested, and we're going to get our catchment area in here and several other things that actually we're not going to be interested in them. Yeah. Okay, so we get the DM, the only input, the DM. We forget about all the other additional inputs. There's no need to fine-tune any of the parameters in here, right? Just click on run. And there we go. Right. You know, there are many other different parameters that we can use for many things, like the flow path length. That means like it calculates the length of the flow from each point up there. If the water is coming from far away or not, that has some relation to the erosion power of the flow. Well, there are many other things. I'm going to get rid of all of them. I just leave the catchment area, which is the one that I'm interested in. And you see it's the same that we had yesterday. Actually, the layer that we had yesterday, we just a little piece of it. here. It's this layer that doesn't show a lot of detail because the distribution of values is not even, right? So the values, we have a lot of values with a lot of pixels with low values and just a few pixels with very high values. And you can clearly see the structure of the stream network, right? So this pixels in white, they're actually pixels with high flow accumulation, and that looks like the main river. This is actually the main river in the area, and then all the other rivers that go in there, right? So you get the idea. As basically, just looking at the detail elevation model, we have been able to make an analysis that actually tells us where the rivers are going, which is a pretty interesting thing, right? Well, you don't need a layer with rivers. If you have a detail elevation model, you can figure out where the rivers are, right? Because of just the configuration of the terrain. There are many factors that are involved in creating a river, but the most important of them is actually the relief, because it's also created by the rivers themselves, right? So you see that. With processing itself, or with Saga, or with the data, the thing is that when the layer is open, these values that I have in here, and that are different to the ones that you have, are not actually the values, the minimum and maximum values of the layer, but the minimum and maximum values of the color ramp that I'm using, right? So the thing is that I have values that goes from 625 to 8 million or whatever it is, the maximum, not that one, the one that you have. But for some reason my QGIS, and I get Martin's ones as well, it's doing this cut, it's doing a tail cut. So it's a thing that it's sometimes done in images to enhance the contrast of image. So if I have my data distributed, I just cut like 2% on each side of the distribution, right? So it's cutting the 2%, and it's actually cutting that 2% of higher values and the 2% in the other side. So if you select this and cut 2% on both sides, these are the minimum and maximum values that you get. But if you use the min-max, which is the one that probably your computers have, then actually I get the maximum value, right? So I'm just changing the, well, not me, QGIS automatically for some reason is changing the range that is painting for rendering, the range that is using for rendering, and it's cutting those 2% on each side, and that's what was driving me crazy. So, okay, so it's correct, we have the values, and now if you generate, if we use that for calculating, even if it doesn't show up in there, it's going to use the right values. And to check that, I just did the statistics, and you can see the statistics of the layer, and actually the maximum value is the correct one. So it's not that one. That is the maximum one used for the rendering, so anything that goes beyond that value is going to be in white as well. Okay, and by doing that, I get more detail, right, in my things. It's another way of increasing the contrast, as I say, with the images, but it's also used with data as not an image, and it has a similar effect to what we saw with the logarithm, right? It's called a tail cut. So I'm cutting the tails, both sides of the distribution. Okay, so we get the catchment area. Let me put the other way so we all have the same thing. Actually. So now it's less informative, as I said, just a few cells, just a few pixels with high values, and most of it is black, right? So we have this. I don't have it because I removed it. Let me calculate it back. So now I have the slope in the correct units. I have the catchment area, right? And I have my detail elevation model, which I'm not going to need anymore, because now my next step doesn't use the DM, it just uses slope and the catchment area, and I go into the topographic wetness index, right? So starting from here, I computed the 2 intermediate layers that I need, and those are the ones that I have to feed into the topographic index algorithm, right? So we search for it, topographic wetness index. Yeah, don't worry about that, this is in my system, problem with the help. And now you see a slope. There's no problem. I have the slope, right? I have to select it in there. I already computed it. Cool. The catchment area. Here is the catchment area, right? In this one, we are calculating the catchment area. We don't have the specific catchment area, right? And so we have to divide by the cell size. So you select 1 in here. Number 1 is 1 divided by cell size. So we're going to use that. Because this algorithm doesn't actually take the slope, it takes the specific one. And this is a way of calculating the specific one. And we're just going to get one result, the topographic wetness index, right? This is very simple. I mean, I will now explain you the idea of the topographic wetness index, right? It's pretty simple, actually. So we just run it here. And we just get it. Right, this is the topographic wetness index. We can just change the palette and have a different color. So what is this index? Just so you know, I'm just calculating this so we have a workflow actually, but I'm going to explain it to you. This index just tells me, based on the topography, what is the probable wetness that I'm going to find in the soil. And how does it calculate that? There are 2 factors in here. One is the catchment area, the other one is the slope. How do you think that the wetness might be related to the catchment area? It's a positive relation, right? If there's more catchment area, that means more water is coming to me. You know that the soil is more likely to be wet, right? There's more water coming, right? What happens with the slope? It's just the opposite, right? It's a negative thing. The more elevated the slope is, if you have more slope, the water is going to run down, right? So the soil is going to be less wet, right? So if I have a place where I have a lot of catchment area and no slope, water is going to come there and it's going to stay there. So the soil is going to be wet. If I have an area that has high slope, it's pretty hilly, like that, and there's no catchment area, you know, there's not a lot of water coming, and the water that comes goes away, right? So it's going to be dry. So that's basically the idea, and the expression is pretty simple. It's just taking the catchment area and dividing it by the slope. Actually, that's wetness index computed, right? I explained you the idea, the meaning, more or less. There are other indexes that use the catchment area and the slope. One of them is called a stream power index, which is just similar thing, but you know, it tries to tell you how the erosion that might be caused by the river, by the water flow, and it's just using the same similar approach. If there's a lot of water coming, then it's going to be very erosive. If the slope is high, then the water is going to flow fast, so it's going to be more erosive. And that's basically, instead of dividing the catchment area by the slope, it's just multiplying them, right? So you can see that this very simple indexes, actually I can do them I can compute them on the raster calculator. I can just calculate my slope, calculate my topographic index, and then I go to a calculator and just multiply the 2 layers, or divide them, right? So, but we have these models with make it easier, but actually they are pretty simple. Yeah. So we've been doing normal things with processing, trying to do this, right? We're on 3 different algorithms, easy, similar to what we did yesterday. Now we're going to get into new things. Now we're going to try to put this into a model, right? Now we're going to do something different. No, we're not going to see new algorithms. We are going to see a new way of using algorithms, right? The only way that we know by far is just so far we just know how to use them from the toolbox, but we're going to see different ways of using the same algorithm so we can do more things with them. So we're going to open the modeler actually, and let's go to processing, and we have an entry there, the graphical modeler, right? The graphical modeler. And we're going to open that. So this is the modeler. When you open it, it's basically an empty canvas. And the idea here is to draw this, okay? This is what I've been doing. I have it in my Blackboard in here. And let's tell processing that I have this workflow and that I want to go from here to there, right? So there are 3 pieces in every processing algorithm. And what I'm going to create here is actually an algorithm. So you have three pieces in here. One is the input, or the inputs, several inputs, right? So that's what do I have to ask the user, right? If you open any processing algorithm, you're going to see the parameters, right? Those are the inputs, the things that I need the user to tell me in order to compute whatever, right? The inputs. In my case, I just have one input, the digital elevation mode. I don't need anything else, right? There are some parameters that I need to adjust that, but I can hard code them, like the method for the slope. I'm not going to ask the user. I'm always going to use one method, and I select it, right? Same with the catchment area, right? So that's it. Inputs, one input. Then I have the process itself, okay? Which are the algorithms that I have to run through? And I have three of them: slope, the catchment area, and the topographic index. I got three processes, right? And then the last thing is the outputs. There are many outputs being generated in here. The slope, I'm going to use it actually. The catchment area, I'm going to use it. Then these algorithms generate other outputs that I'm not going to use at all. And this one generates the topographic index. The slope and the catchment area, I'm going to use them, but I don't want to keep them, actually. The only thing that I want to have is the topographic index. So I basically want to put this schema in here, this idea, into something that goes from a DM into a topographic index. That's everything I want. So I want to hide all the complexity in just one thing. I give this to the algorithm, it generates that. Nothing more than that, right? So in the end, I should end up having a dialog that asks me for one layer and generates one layer. And I just hide all the complexity inside, right? So I'm not going to give the user the slope or the catchment area or the aspect that is calculated in this same algorithm. No, I just take the DM, generate the TWY, right? So it's as simple as it can get, right? And this is what I'm trying to do. What I have to do is to define these pieces, input, algorithms, and the output, right? By using the menus in here, in the left-hand side, right? This one called input, and this one called algorithms, and the algorithms, I use them also to define the outputs, right? So what do I need as the input? A DM, what is that? That's a raster layer, right? Okay, so in the menu on the right-hand side, I just look for raster layer, and I just click on it. I think it should, oh yeah, it works. Yeah, I added that. I don't know if yours is going to have that, if you drag and drop. No? Okay, I added that like last week or a couple of weeks ago. So, but you just double click on it. Right. So this is my raster layer. I'm going to ask the user for a raster layer, right? So what I have to do is to give it a name, like how I'm going to ask the user. Let's call it DM, right? And we know that when processing uses raster layer, it can be mandatory or it can be optional, right? See, in the case of the catchment area, there were a lot of optional things. Is this an optional one? No, it is required. If I don't have a DM, there's no way I can continue, right? So this is not an optional thing. This is a required, it's mandatory, right? So I leave that to you. And that's everything that I need, right? That's it. So I get one piece in there. Just one piece that I can move, and then I have to link that. So I have this. Now I have to start adding these sort of parts, right? Okay, no more inputs. That's everything I need, right? That's it. I'm going to go to the next block of things, which are the algorithms. This is what I have to add now. 3 algorithms. This is a very simple model. Later we're going to do a more complex model. You are going to create a more complex model. So we move to algorithms, right? And here what we have is our basic toolbox again, right? See that in here you don't have the check, this drop box to select between the advanced mode and the simplified mode. It just takes the mode that you're using in the toolbox. So if in the toolbox you're using the simplified mode, you will have the simplified mode in here. I was using the advanced mode, so now I'm seeing the advanced mode in here, right? Okay, so it's the same as we did before, right? So the idea is that instead of going through all the process, several times. I mean, each time that you want to calculate a topographic index, you just go through all the clicking once, and then you just get your model done, right? So I'm going just to do the same thing as I did before. First I'm going to run the slope, then I'm going to run the catchment area, then I'll put it all together in the topographic index algorithm, right? So let's go for the slope. Same, I can look for it in here, no problem. Well, so things that are worth mentioning here. This is the same, mostly the same. It looks the same, but it's slightly different to what we had before. Okay. The first difference is that you don't have a log tab. Why? Because I'm not going to run this algorithm, right? The log is the information about how the algorithm is run. I'm not going to run it. I'm just defining the conceptual model, right? I'm not going to run this algorithm. I'm just going to put a piece in this. I'm going to draw this structure, but I'm not going to run it. When it's finished, then I will run it, but not now. Now I don't want to run the slope aspect curvature algorithm. I just want to add it to my model, right? So there's no log tab. Second, if you just extend that drop-down list, you will see that all the layers that I had, all the layers that are in my QGIS project, they do not appear there. Why is this? Because I'm not trying to run the algorithm. Once again, I'm just defining the algorithm conceptually. So what I see here is the raster layers that are available in my model. And I just have one, the one that I'm asking the user to enter, right? So then this is going to generate more raster layers. So the next algorithm that I add, it will have this as options. But we're not talking about layers, like real layers here. This is the conceptual layer, right? So it's an abstract idea. So I just get in here the layers that I have available. This case is pretty simple. I just get the DM. So I want to link my algorithm, see, my algorithm, I want to link it to the DM, right? I want to put the DM into the slope algorithm. This is what I'm going to do. I'm telling, for the elevation, you use that one, right? That's it. And then you see the outputs. The outputs, it tells me if it's an output raster, output vector, whatever it is, right? But here I don't have to enter the name where I'm going to save it, because once again, I'm not going to run the algorithm, right? I'm just defining the idea. So what I have to tell is, remember what I said, inputs, algorithms, and outputs. If I want to keep an output, I just add a name here. If I don't want to keep that output as a final result, then I don't do anything, right? I leave this empty. I leave it blank, okay? So do I want to keep any of these things? I want to keep this slope, aspect, curvature? No. I'm going to use them, but the only thing that I want to keep in the end is this, right? This is the only thing that I'm going to show to the user. Like, this is the output. And then the user will select the file where he wants to save that, right? Yeah.
If we wish to keep one of the layers, where would we then, where would this small processing model save the layer?
If you want to keep that layer, you just add an aim in here.
Yeah, but how do I know where the computer saved it?
Because that's a different thing. Okay, let me put it like that. Let me show it to you. See, I'm not adding anything, right?
Yeah.
Okay, just add it here, right? So let me save that algorithm so you can see the steps, right? This is going to be called TWI from DM, right? And the group name is whatever, my models, right? So now I save it. Save model. In here, this is my models folder. Okay, in here, TWI. Right?
Okay.
Now see the idea. I ran it. I ran it. There's no output. This is what I'm showing now to the user. You know, it's automatically generated, right? I'm taking a DM and I'm not keeping any output. Now let me change that. Oh shit, this crashed. That's not a good thing. Let me see if I can update my models in here. I'll do it again. The idea is that if I put like keep that, then when you run it, the user, when you say like keep this algorithm, that means ask the user where he wants to save it. If not, the user doesn't know anything about that. It's like you know, all the internal complexity of the algorithm, right? That's the idea. I don't know why this crashed, by the way. But let me do it again. Add that, and then I add the slope now. So if I add a name in here, then the user will have the option to run that, right? So if I have this as slope, right, whatever, you know, I have that, I can run it, and you see now the user has the chance in here, right, to see where it went. But I don't want to keep it anywhere. I don't know if this is going to crash or not, if I edit or no. That's fine. I keep it, that's empty, right. Okay, so I have my first step in here, right? I'm going to try to put it in the same thing.
There was also one difference that the default method was set as a 0 maximum slope instead of 5, which you said that is by default.
You can set it to whatever you want here, actually. Yeah.
There's a difference between when you use.
Yeah, one takes like some default. That's the thing. One thing that I can do is I can actually put that out, so I can let the user select this, but I don't want to in this case. I'm just going to fix it. I can, you know, all these parameters, let the user like take them out of the model, but I'm just keeping that actually. So I have this one. You see, you can extend that. You see, I got all these outputs. They're not linked to anything. The DM is linked to the elevation, right? So I can see it in there. You can expand and collapse those things. So the next step is the catchment area. So no problem. What is going on with that? Oh yeah. Okay, I'm going to have the Python console in there. It's ugly, but I need it because, sorry, this is my test processing, and it tries to put a lot of debug stuff on there, and if I have the console closed, it's going to break. It's going to crash, so sorry for that. Let me do it again. Keeps on crashing. So DM slope. Catchment, that's it. So now in the catchment area, I do the same thing, right? Input, I just need the elevation, right? The elevation goes into the catchment area, right? I can leave the other ones as optional, right? You see that in this case, when you have a number, we're going to use that later. So you are going to use that later. In the case of having a number in the algorithm, when it's run from the toolbox, you have the text box where you can type the number, and then you have this button to pop up the calculator, right? In this case, I have the number, the text box where I can put it, and this is a drop-down menu. Why? Because I can ask the user to enter values, okay, and then I can link them to here. So instead of me typing, I leave the user do that. So it's a bit different. We're going to use that in the next exercise that we do, actually. So I just can keep everything as it is. And once again, I'm not keeping any of these outputs. I'm going to use one of them into that one, but I'm not keeping it. I'm just keeping the TWY, and until I reach this point, I don't need to keep anything, right? That's it. If you wonder, this parent algorithms, we're not going to use that, but you know, if I do this structure, right, that means that this algorithm cannot run until I have this, or this algorithm cannot run until I have this. Sometimes you don't have something that is going from here into here, but you have to wait until this one is done to run that one. So then you use this parent algorithm. So you can tell it, wait until this is done before running this. We're not going to do that because now this dependency is implicit in how the inputs go into the next algorithm, right? Okay, so we get this, the elevation. That's the only thing we need. We just click on OK and do it, right? So you see, from all the inputs it takes, I just linked my DM to the elevation. There it is. Let me put that here. So now we have the last algorithm that we have to put. Is the TWY, right? In here. Okay, let's look for it. Easy. And now what do I have? I do not have to use the DM here. I have to use the slope. But I have a slope already. Why? Because I have added this algorithm, and this algorithm generates a slope. So if I just take that down, that drop-down list, see everything that I have. Like I have the DM, I'm asking the user for the DM, I have the slope that is generated by this algorithm, the aspect, the curvature, etc., etc. Then I have the catchment area from my algorithm called catchment area. So all the things that are generated by the previous algorithms, I have them available here, right? So all these pieces are generating outputs that now I can use as input, right? So I'm going to use the slope in this first field. So is it as a slope? I use the slope from the first algorithm. Makes sense? That's why we were adding it. Same with the catchment area. I add the catchment area from algorithm 1, right? Change that to 1. Remember, we have to convert to this pseudo-specific catchment area. And that's it, right? That's it in terms of inputs. Like I've designed that actually, just like, you know, joining these two algorithms into one. And now, what do I want to do with this result, the topographic wetness index? I want to keep it, actually, right? This is something that is the final result of my model. So how do I want to call it? What is the name that I want to show to the final user? Let's put it like TWY, simply. It's like, so I just put the name on it, right? So I'm telling the algorithm, like, use these outputs from here, from this algorithm and the other one as inputs. Do whatever with these values, and whatever you generate, I want to keep that. Ask the user where he wants to keep that. Do not save it into any file, temporary file. Just ask the user, okay? Because this is something that I want the user to know that I'm generating that, right? That's it.
Don't you have a dependency?
Where?
The topographic wetness index can't be run before the.
Yeah, that's what I was saying. Like, there's a way of adding a dependency, like explicitly, but in this case, like the modeler knows if there's a dependency, right? Okay. One case of the other. In this case, I mean, this cannot be run if this is not run, right? But imagine that I have a. Let's say I have an algorithm, for instance, that you can add in processing that makes a SQL query to a PostGIS database, but it doesn't get any output. But I have to do that, and then there's another algorithm that has to do whatever on the PostGIS database. So this one has to wait for the first one, but there's no way of knowing that they are related. So I just add them explicitly. So like, this one is making the SQL query, wait until that's done before you do whatever on the database. Right? In this case, it knows, right? You know, it sees that there are. Yeah. Yeah, that's it. In the other case, I can add an algorithm that is floating in here, not linked to anything, right? So that's the way of saying, like, no, wait for that one, okay? It's a different thing. So you see that now, when I declare my output, it actually paints a new thing in here. So this is my same schema in here, and it's generating the TWY, right? So this is my model. I just write it once, and then I can run it as many times as I want. From a DM, I'm going to get the TWY, right? We have to save it. So we enter the model, TWY from DM. We enter the group, my models, right? And we save it. And this is important to know. The place where you save your algorithm, you can save it whenever you want, wherever you want in your system, right? But if you save it to the first folder that comes up, this is the models folder. And if you save it in there, your model is going to be in the toolbox. If not, it's not going to be in the toolbox. So you just, in my case, by default, it has put my folder in here in the desktop. But you can put it. I will show you later how to do that, right? I will show you later how to change that. But just in the first folder that you see, I don't know which one is in your case. It's it's called models. That's perfect. That's the one where it has to be. Okay. Just put it in there in that models folder, right? So you just put that in your. Actually, I'm going to put that in my models folder the same, and I'll show you that. So it's here, QGIS Processing models. So I'm putting this in my models folder, and I call twy.model. right? Model was correctly saved. Now you just close. And you should have your model in here now. See, in your models, you should have your model in here. You have a new algorithm, but it's not a one that comes from Saga, it's not one that comes from QGIS, it's one that you have created, right? One important thing, as I said, is to know where your models are stored. And if you go to, in here, you go to processing, and the options of the processing framework, remember we've been there a couple of times already. In the models, you have a models folder entry, right? By default, it's going to point to that model folder that you have. But if you want to put it somewhere else, just change that, right? You have to know that if you save your models in a different place, they're saved, but they will not appear in the toolbox. If they are in your models folder, then when processing is open, it will go to that folder and load all the models and show them in the toolbox, right? So in my case, I'm going just to make it point to there. So I should be seeing, let me check. This is a select file thing. C users Olaya slash. Let me check that. C users Olaya QGIS tune processing models. Just like that. Right. Okay. So we have our model now. Let's run the model, right? Let's run our model. That's the interesting part. Now if someone comes with a different data set, like here is my DM, I want the topographic index. You don't have to go through every single step. You just go to your model and see, it's give me a DM, I give you a topographic index. Okay? Internally it's going to do calling this, and calling this, but you don't see it. That's internal, right? Okay. Now this might not seem very useful for you because there are 3 steps, but now when we get into the bigger model with hydrology, we do 6, 7, 8 steps. It's going to be more useful. And imagine a process that you have 50 steps. You know, you put 50 steps into one single step, right? So that makes a lot of sense, right? So let's run it. It's just pretty easy. You just run it, and you see that it runs catchment area, and now it runs the topographic wetness index, it does whatever, and voila, I have it here, right? One click, I got everything. So you have been like kind of programming, you have been programming a small algorithm, but not typing the code, just doing it graphically, right? You have been combining different algorithms, asking the user to provide some input, etc., right? More serious hydrology. We're going to take our DM, we're going to calculate the catchment area, we already have that. Then we're going to try to, instead of just having the catchment area where I can see where the rivers are, I'm actually trying to get a real channel network, the network of all the rivers as a vector layer, right? And then I'm going to try to compute the watersheds associated to each one of the parts of the river, and I'm going to try to compute some parameters for each of them, going to do some real hydraulic analysis, analyzing all the system of different watersheds and calculating stuff, right? So I'm going to add several steps, right? I'm going to do something that takes several steps. It will take us a while. I don't know what time it is. Let's see, let me check. I still have time. So I'm going to do that, and then once I finish that, I'm going to give you some time so you can create a new model much larger than this one that we have created to do all the hydrological analysis in one single step, right? Okay, so just take out everything except for the catchment area and the DM. Okay, so first thing we're going to do is try to find out the catchment network based on this catchment area layer. What we're going to do is to apply the next idea, right? The cells, I already mentioned that, but the cells where the catchment area is high are more likely to have a river. The cells where the catchment area is not high, is low, they're not cells where I'm going to find a river. So I'm going to set up a threshold. It's like, if catchment area is above that, I consider that it's a river. There's a lot of water coming, so that's going to create a river. If below that threshold, I consider that, you know, there's some water moving in there, but that doesn't create a river, right? So I'm going to set a threshold and use that, right? This is the criteria. And to apply that idea, I have another algorithm also coming from Saga, which is called channel network, that is going to allow me to do that, right? So let's look for channel network. Okay, and you see it's one of those algorithms that have a lot of inputs. It's not a simple one, right? Don't worry. Some of them we can, you know, ignore them. Some of them we can take them, you know, use the default values. There are two important things in here, two important layers. First one, of course, is the elevation. We're always going to need the elevation because, you know, we are analyzing, we're doing terrain analysis, so we need the terrain, right? We need the elevation. So in the elevation, we're always going to put our DM. Remember, it's a hydrologically correct DM. We need a hydrologically correct DM. In this case, if not, you have to go through the field sync process in advance, right? Flow direction, if it's optional, we can not use it. So I'm going to leave away all the optionals just for the routing. And, you know, I leave that. Right. Now there's an initiation grid. That means where are rivers initiating? Where are they starting? Right? Which parameter I'm going to use to select if a river is going to start or not? That's what I mentioned. I'm going to use the catchment area, right? I'm going to look at the catchment area, actually, and to do something like that. Looking at the catchment area, like, I go downhill, no, the river doesn't start, and when I reach a point above a given threshold, like, yeah, here the river starts. And then I just trace it downhill, right? So this is what I'm going to use as my initiation grid. My initiation grid in here, I'm going to use the catchment area, right? That is, I'm going to apply that criteria on this layer, right? Let's try that. And which is the criteria? What kind of criteria I can use? Because there are many different grids that I can use, many different variables I can use for that. So what is the criteria that I'm using? It's less than or greater than. I mean, it's when I get beyond a value, above a value, that's where it starts, or when I get below that value is when it starts. In our case, it's when it goes above that value, right? So it's greater than. So when, sorry, I didn't do it in here. This is the catchment area. So I'm saying like, this is a DM. When the catchment area is greater than this threshold, that means that the river is starting at that point, right? That's the header of the river, right? You get the idea? So I go downhill. It's like, no, there's not enough water, and I reach a point. It's like, there's enough water in here. From now on, this is a river, right? So that's what I'm doing. So I'm going to have to put the threshold, and it has to be something in the range of the catchment area, of course, which goes from the simple area of one single cell, you know, those pixels that do not have anything uphill, right, to the large value downhill. And how do I select? Yeah, I got so many things in there. Let me close all this. Yep, okay. And how do I select my threshold? Well, this is a matter of basically trial and error. So, because it depends also on what you want, right? If I put a threshold that is very low, there are many pixels that are going to fulfill this condition, right? So that means that I'm going to have a lot of channels. If I put a very large value, my river is going to start just in here when I reach the very high value. So I'm going to get a very short and not very dense network, right? So I can try with different values and see how that changes, right? And in the end, depends on what you want to do. If you're analyzing a small watershed like this one, you can select a different value. If you are analyzing the watershed of a big river, right, whatever, the Mississippi River, then you should take in a threshold that is larger, so you don't get all the tiny rivers. You get just the main one, right? So it depends on what you're going to do. It depends on the scale you're working. Remember what I told you the first day about the scale? Depending on that, you might choose one or other's initiation threshold in this thing. The units of the threshold are, of course, the same units as the catchment area. The catchment area are square meters. That's why the minimum is 625. That's 25 multiplied by 25. That's the area of one single pixel, because I have a cell size of 25, seen here, damn 25. Right? So I get how many square meters do I consider that it's enough to create a river? And we're going to start with 10 million, actually. And just 10 million. So if I have more than 10 million,
How many zeros did you say?
6.
10 million.
There should be 6 zeros in there.
Yeah,
7, sorry. So that means that if my area is above that, then I start a river. If not, that's not a river, right? Then I can ignore the other parameters. Don't worry about those ones, right? And then you see I'm generating now more than one layer. I actually have 2 of them called channel network. One is a raster layer, the other one is a vector layer. Right? Because I'm generating the raster layer, which is like no data everywhere except for in the rivers. And then I have the vector layer, which is a real vector layer with lines, actually, that I can use for different things. Right? I'm actually not going to use the vector layer later. I'm going to use the raster one for the catchment areas and all that. Sorry, for the watersheds. But we're going to calculate the 3 of them, and we'll have a look at all of them. Right? So just summarize it. This is what we have. The elevation, and I take this, and based on this layer, if I get a value greater than this value, then starting from that point, I start a river, right? I go from that point, when the value changes from less than this to greater than that, and I start tracing my river downhill, right? That's the idea. So let's run it. That's what I get. Right, you see, this what you see here is the vector one, right? Channel network, channel direction, the other channel network. You see, that's what I get. I can actually take those away. So you see, you can see it more clear like that. So I have just created my vector layer based on that threshold. There's the main river, then there are 2 other rivers in here. Right? But I got this main river. So now let's try with a different threshold. Let's try what happens if instead of 10 million, say just try 1 million. Right? What do you think is going to happen? Here the value is 10 million. So if you have to go uphill, there's less water. So the rivers are going to start a little bit sooner, right? If I go downhill, okay, here it starts. Instead of here, it's going to start in here. And I'm going to see more rivers that actually are not considered rivers that are going to appear in that. So I'm going to get a denser channel network, right? So let's do it. Let's try it. Yeah. And let's just go back. I think yeah. Okay, I didn't put the DM in there. Sorry. Channel network. Sorry. Catchment area. Greater than.
Now we assume that it's based on evenly distributed precipitation. What is it if it's very different distribution?
If the precipitation is different when you go to your catchment area, I mentioned that before, you have this weight layer. So when you calculate your catchment area, you can instead of giving the same weight to all the pixels, you just give your weight depending on the precipitation, or if your catchment area, you actually are not interested in the amount of water that flows, but in the amount of sediments, you can just weight it with a layer that you have on how much, the amount of sediments that are generated on each pixel. So you just can weight it using that. in the catchment area. But once we get to the next step, we're also already using the catchment area. So you see, now my network is a little bit different, right? There are more rivers. There are way more rivers, right? Actually, what I'm going to do next is to divide the space in here, divide this big watershed into sub-watershed based on this river. So I'm going to add one here, another one from this part. So the density of this channel network is going to affect the density of the set of watersheds that I'm going to calculate next, right? Instead of using this one, I'm going to use the other one, so it's clearer and I just get just a few watersheds. With this one, I'm going to get many little watersheds, so I'm going to go for the other one. But you know, you get the idea that the threshold actually has an influence on how the watershed is later computed, and how the channel network that I create is, right? Any question? You understand more or less the idea how we're getting the network, right? We use a parameter that actually shows us where the network is. So let me get rid of those ones. I don't need them anymore. So actually our catchment area gives us an idea of where the rivers are. So I'm going to use this layer to actually get the channel network itself, right? So we get it, okay? Okay, next step, we're going to go for the watersheds now. We're going to get vector layers, like vector polygons. We're first going to go through raster polygons, then vector polygons. We get these polygons representing all the points that if I put water on them, they end up flowing to the same point, right? And I just go for watersheds, watershed basins. Right. So what do we have here? We have the elevation, the channel network, a raster layer. It's not the vector one, it's a raster one, right? So it's going to use that raster one to know, because what it's going to do, it's what we're going to do is, if I have my network, right, in my raster layer, it's going to have no data all over the place except for in this cells that actually form the river, and it's going to find the junctions in there, right, and then use the junction as the closing points, like the end point of the watershed. So then it's going to give me like the polygon in here, the polygon associated to that one, then the polygon associated to that one, and that one, right? So it's just going to divide that based on all those points where two streams meet, right, in all the junctions. So I need the elevation. As I said, we always need the elevation. We're doing terrain analysis, we need the terrain. Channel network, well, we have one that is called channel network, generated by the other one. Once again, see the CRS, I remind you of that. We're always getting the same CRS that the layers that we put in, right? This is optional, we don't use the same root. Minimum size, that means that if I have 2 points very close together and the watershed is very small, it's not going to create it and link it or join it to the closest one. If we enter a minimum size of 0, that means that I want every single one, even if they're small, I'm going to go for them, right? And finally, it's going to generate the watershed basins, right? So that's it. So let's go for it. That's it. You see, I can put the rivers on top of that. It's going to be more clear. Yeah, you can clearly see that when there's a junction, it just use that as a closing point. Voila, voila, and that's that, right? So I'm dividing this into hydrological units. Dividing my space with the region that I'm analyzing into that. See, there's some no data in here because it doesn't belong to any place. This flows outside of the TM in here, and I don't know what it's upstream, right? Okay, so what is that? Is this? That's those watershed that we have, but that's a raster layer, right? If I see, it's a raster layer with all the values corresponding to a single watershed. They have the same value. I can just check it in the view identify. So you see, if I click here, they'll have the same value. 7 in this case, 5 in this one, 4 in this one. So it's like single values for all the points in here, right? It's nice to have it like that, but it would be much better if I had a vector layer, right? If I had real polygons that I can use, and then I can do things with them, and I can add attributes to them. Like for instance, like the average precipitation each one, the average elevation, or just calculate some stuff in there, right? So now I'm going to let you do some work. You know, I explained the hydrological part. Now you're going to try to do some more generic GIS work. I will do it later, but I want to give you like 5-10 minutes to do that. And I would like you to turn this into some vector polygons, right? Instead of having raster. And then see if you can get me in each of them. You know, we've been discussing about the topographic wetness index, the average topographic wetness index in each one of these polygons, right? So that's the idea. Turn this raster blobs in here of the same value, these groups of pixels, turn them into vector polygons, and then try to calculate the average topographic wetness index for each one of them, right? Shouldn't be difficult. Just like if it doesn't happen, it's fine if you don't get it. Just, you know, I just wanted to spend 5-10 minutes trying to find out something by yourself, so I'm not the only one doing things here. So that's good. We have a raster layer with something that looks like polygon, and we want to vectorize it. It's easy. So here, which one we want to vectorize? The watershed basins, right? That's it. And we want to vectorize just a given class, just those pixels with a given number? No, we want to vectorize all classes, all different polygons that we can find in the raster layer, right? So we are not using the class identifier, it's not going to use it, right? If we have classes that have multi-polygons, how do we want to vectorize them? But in this case, we don't have any multi-polygon. Of course, we cannot have multi-polygons in here, because if there are pixels that belong to the same watershed, they have to be together, right? Because they are hydrologically connected. Okay, so that's not important in here, right? So that's it. It generates some polygons. Voila, there they are. Notice in here one important thing. This black. Why is not a polygon in there? I mean, I can see there was a polygon in there, right? Why do I don't have a polygon in there? I mean, this is a polygon, right? Why? Anyone knows the answer to that?
I guess that the cells has no value.
Yeah, there's a no data value in here, actually. So the no data value is ignored. It's not used to, I mean, there are many cells with the same value, but it's a no data value. So that's true, right? It is not because it's close to the border. See in here, we're close to the border and it works, right? But it's just because it's a no data value, right? So those pixels in here do not belong to any watershed. So that means that we cannot give them a number of the watershed they belong to. So that's okay. So I have my polygons now, and I said let's calculate some average value, and I can also do that. And you see this algorithm in here, grid statistics for polygons. That's cool. I look for, what do I want? A statistic. So I type stat, you know, just get just 15, 20 algorithms. I can read them one by one. Oh, this one is the one that I need, right? Grid statistics for polygon. It takes grids, it takes polygons, and computes the statistics of that grid within the polygons, right? Okay. Of course, these polygons in that grid, they have to be in the same CRS, okay? Otherwise, they're not going to match. They have to match. So the polygon actually falls into the grid, right? Not a problem in this case. We're generating all the stuff ourselves from the same DM. so they're going to have the same CRS, the 23030, but yeah, make sure that you don't forget about that, right? Okay, and I don't have the TWY, but I'm going to calculate it. It's no problem. I compute it from my DM using my model, actually. Here we have it. Right? So I just now compute the average of the TWY, the statistics of the topographic index within the polygons, right? Okay. So the polygons are my polygons, right? And now I select which values I want. I'm just going to say no to almost everything and just get the mean, right? Just the mean, right? Okay. And I use the TWY. I can select as many as I want. It's going to calculate, if I select 5, it's going to calculate the average of the 5 of them, right? So these grid, topographic wetness index grid, in these polygons, I just calculate, sorry, not the maximum, just the average. Okay. And I get a new layer, and if you go to the open attribute table, I see, you know, in here I get the average, right?
Color the polygons by the
Oh yeah, sure.
PI value?
Sure. You just double click on that. You just get to the symbology and you select in here the graduated scale. It's a continuous value. So I just go from, let's say, this one, but inverted. So green is going to be like a low value, red a high value, like there's more erosion risk in that. That should be. Sorry. I select that one. That's it. You have it. It's pretty simple, actually. But you see that the ones I have. If you want to do that again with the higher value of the lower value of the threshold, you're going to get more basins and you get different, but you get the idea. Okay, so let me put this into a nice workflow. Instead of the topographic wetness index, we're going to work with the stream power index, what I mentioned before, right? So we have a DM. From the DM, we go to the catchment area, right? We should go to the filled sinks, but I'm skipping that, right? I go to the catchment area. Then from here, I go to the network, right? From the network, I get the watersheds. Then I vectorize that. I get polygons. And then with the polygons, I get the statistics, right? Using my stream power index, right? What I have here. And the stream power index, I calculate it with the slope and the catchment area, right? And to calculate the slope, I use the DM, actually. So you get this with the DM, I calculate the slope. The CA, with the CA and the slope, I calculate the stream power index. And I go all this way, and I finally get that. This is my final result, right? You get the idea? Now you put it in a model. If you were among the super smart guys, you probably didn't write your own model, and you find out that it's already one of the example models. So actually there was no need for you to write it, but if you want to check it, you can check it on the screen, or in your system you have example models. Yesterday I told you that we can save a raster layer and save it cutting it to a given extent. Remember when we have this layer with a lot of no data, and you asked like how we can get rid of those no data, and I told you, well, it's easy. You can just zoom into a given area, right? You zoom into this area, right? And then you just go to save as map view stain, and I save this layer, right, with extent. And let me do that. Reduced .f, right? I'm just saving that one. Is it fine? Yeah, it is.
Oh, you have the pixels. You have a pixel size threshold.
Yeah, the normal tool. Yeah, that's fine. Let me change. Let me now load that layer. Reduced 1. So now I have this small part, right? Okay. And now I calculate the catchment area, right? Of that one, of the reduced one. That's the catchment area, right? What's wrong with that catchment area? That is not a correct layer, but just think about it. What do you think is wrong with that? I mean, I just took a small piece and I did the same, right? I can do like my catchment area, my everything, just in there. Why do you think this is not correct? I can tell you that it is not correct. So just so you think about it. For those that you have finished with the other thing, think about, in terms of hydrology, why that layer, it's absolutely useless.
There's some of the issues.
You're missing what?
You're missing part of the watershed.
You're missing part of the watershed. Actually, that's it. Good question. That's it. You're missing part of it, and it is, you can say that this part of the layer, they have something that is called edge contamination. When you start from a point and you go up, 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 and you reach the border, you don't know what's going there, right? You don't know if there's just one single cell or you have the full Mississippi River upstream, right? There's an algorithm, if you want to have a look at it, in Saga called edge contamination, actually, which basically is going to tell you which cells, which pixels, if you go up, it will eventually reach the border. That means that this parameter, the catchment area, is invalid in that part, right? So yeah, that's it. Correct answer.